So let's just go over chemical equilibrium. So what is it? So whenever we're saying a reaction is in chemical equilibrium, what do we basically mean? Do we basically mean that the reactants and the products are equal in concentration? And of course, let's base our understanding on this kind of a reaction where we have A plus B giving us C and D. That is in a chemical reaction. And then of course this is not a forward reaction, this is like both forward and backward reaction. So that's the kind of a reaction that we are trying to talk about. So what do we mean when we say it is in chemical equilibrium? Do we mean if all the concentrations are equal in terms of the products compared to the reactants, or what do we basically mean? So now, if you have 2 molar concentrations of all these products and reactants, do we say the reaction is in chemical equilibrium? Of course not. Okay. So now, chemical equilibrium basically tells us to say that the rate of the forward reaction and the backward reaction are the same. Not that the concentrations are the same, but the rate of the forward and backward reaction occur at the same rate. And what basically happens is the idea to say, thinking of it in the case where you have 2 molar concentration of the reactants, and then for the sake of understanding, I'll use the same as well on the other side. I'll use the same concentration for both C and D. Now, if we are saying this is in chemical equilibrium, the concentrations will not change. The concentrations will not be changing. So if it means that 2 molar concentrations of the reactants are converting, and then what it would mean is as well 2 molar concentration of the products should also be what? Converting. Not necessarily that this is the case in other situations, because as you will see from our examples, you notice that necessarily if 2 things are reactants doesn't mean that they should have the same concentration. You find that maybe one is 1 molar concentration and one is 0.5. But for now, let's look at this kind of a situation. So if we have 2 molar concentration converting back to reactants and 2 molar converting to products, and then you notice that there will be no change in what? In the concentrations of these reactants and the products. So this is what we call chemical equilibrium. Okay. So now we know that chemical equilibrium now is, you're talking about the rate of the forward and the backward reaction. Okay. So now under chemical equilibrium, we're going to be very much interested and be very much calculating the equilibrium constant, because it's very helpful in our calculations. So remember, under kinetics, I told you to say it's going to make more sense as we get to talk about chemical equilibrium, how we get to find the value of K and what it is. So now, equilibrium constant is K, and then we can say think of any reaction quotient to be Q. So Q is a constant when you are not at equilibrium. Let me not say not at equilibrium. Let me not say that. So Q is a constant of the reaction at any time in the reaction, at any point, whether at equilibrium or not. Now, K is more specifically for equilibrium. So therefore, we can say Q and K should be equal at what? At equilibrium. So for now, take note of that information there. Okay, so how do we find the constant K? So a constant K is basically going to be dependent on the products. So even under electrochemistry, I told you to say it will make more sense when we get to chemical equilibrium. So this is the way it is, products over reactants, and we said you need to make sure that they are raised to what? Stoichiometric coefficients. So in this case, looking at what we have, in terms of our products, we have C and then we have D. So I'll put these in parentheses to show that these are concentrations. So we have C, D. So I've raised them to their stoichiometric powers. So now under electrochemistry, we saw that most of the times we just add like one reactant, one product being involved or being included in the formula. But you see, under chemical equilibrium, we'll talk about cases where we have different what? Maybe even 3 being multiplied on top. depending on the number of products or reactants that you may have. So in this case of reactants, we have A and B, right? So we can raise them to their powers as well. So I'm using the small letters to denote the coefficients. Okay, so this is the way you get to find the constant K. Now, some of the things that you need to notice whenever you're trying to find K, you'd want to make sure that whatever you get to include in the constant calculations in terms of these C, D, A, B, you're only going to use gaseous and aqueous what? States. Anything that is in form of liquid, solid, do not appear in the equilibrium expression. So if you have a solid, let's say A, then it's not supposed to appear under the equilibrium expression. Take note of that information. Very, very important. Always just use gaseous and aqueous states in determining or expressing your K. I think we talked about that even from electrochemistry under the next equation where we had our Q. Okay. So that is about the K. Now just a quick exercise that we just want to help us to understand more. So I'm sure under kinetics we have talked about what we call laterals. Okay. So I've written the same reaction in two ways, where one is like the opposite, meaning that you have a reactant. This is our reactant. In the other case, it's a product. Of course, we do know that this is a reversible reaction from the arrows that we have. Okay. So now, assuming your case C for that function. In fact, even before we can go to that, let's look at this in this way. So we said our rate law is going to be dependent on what? Is going to be dependent on the, so it's going to be K multiplied by what? So this is from chemical equilibrium multiplied by the concentration of the reactant. Now, it should be raised to a certain power. That's one thing that we said. It should be raised to a certain power. So what power? We don't know. Okay. And then again, for the other one, it should also be K, and then dependent as well on what? On the reactants. So now, for the sake of just a bit of understanding, of course we do determine the powers using the experimental data, because it's not necessary that when you have a 1 there, you should also have a 1 there. No. Okay, but let's assume that in this case. So let's assume the power there is a 1, and then here we have a 2. So for the sake of differentiation, I can say, looking at this one, let's consider this one to be our forward reaction. So say forward, and then the other one will say reversible reaction, right? Okay. So if you equate this, I think we did this under a reaction mechanism. So if you equate the rates, because we are saying under chemical equilibrium, these guys are supposed to be equal. That's what we are saying. The rate of a forward and backward reaction is supposed to be the same. So K final N2O4 is equal to KR and then NO2, the power 2. So I can create, let me just create some space, and then we'll see what we are going to have. So we can put the constant on the same side. So I can divide both sides by KR, so that we have that on one side. And then the other side where we have NO2, I can also decide to divide by the other side, which is what? N2O4 from the other side. So this is one way we can express this. So now, looking at that ratio that we have, we can call that to be our K, or equilibrium what? Expression constant. So now, this takes us back to the equation that we just came up with. So if we go back to the equation that we had, I'm sure you're able to notice to say we had N2O4 giving us 2NO2, right? This is something that we had. And what can you see? So what you can see is we're trying to say we've proven the formula from what? The rate rows. That's where it's coming from. The rest of equations. So this is how you get to find the equilibrium. So you look at your products, which is NO2 in this case, and then your reactants, which is just that. And so this is the way you find your K expression. So we've proven it using the rate rows. This is the way it works. So the ratio of that is just what we're calling the equilibrium expression, or constant K. Of course, we've said K doesn't have units, and then K is determined using concentrations of your reactants and products only at equilibrium. Take note of that. Don't use the initial concentrations, only use the concentrations at equilibrium. That's why before the end of this video, we need to understand how we get to find the equilibrium concentrations when we are given the initial concentrations, because at the start of the experiment, the rate of the forward and the backward reaction may not be the same. So obviously, in a case where, let's say you have A and B reacting, for example, to give us C and D, you may find that you're only starting with what? A and B. So there's no way you can have a backward reaction. So first of all, you need to produce some products. And then the products will also start reacting to give you back what? The reactants. So all those things are supposed to happen. Okay. So now we can also find the expression of our K in terms of concentrations and in terms of pressure. So in terms of concentrations, that's what we've already talked about, where you plug in the equilibrium concentrations of the reactants and products. Now you can also find the K using the pressure of your gaseous reactants that you have and products. So in a case where you're dealing with gases, your Kp is going to basically be given as well, going back with the same setup of reactants, where you have A, B to give you C and D, and then of course where they have let me use the small letters or lowercase letters to just denote their stoichiometric coefficients. So it will just be the pressure of A. So I'll say, I'll denote that as PA. The pressure of A raised to a stoichiometric power A multiplied by, of course, this is wrong. Why? Where you're saying it's products of a reactant. So the pressure of C and then multiplied by the pressure of D. These are supposed to be raised to what? The powers C and D, and then divided by. So say again, the pressure of A, the pressure of B, and then these again should be raised to their stoichiometric what? Powers. So this is the way you can use your pressures to find Kp, or your equilibrium expression in terms of what? K. Okay. So now, what is very, very important is for us to understand the relationship that is there between this constant Kp and Kc. What relationship is there? So you do know that there is this formula from the gas laws. Okay. So where you say PV is equal to nRT, and then let's try to make what? We can try to make P to be the subject. So pressure is going to be nRT over what? Over your volume there. Now you have N denoting the number of moles, and then you have your volume. So when you divide the number of moles and volume, it gives you what? It gives you a concentration. So our formula now becomes pressure is equal to, let's say, concentration of something A is multiplied by RT. This is something that we have. Okay. So from this relationship, we should be able to relate Kp and what? And Kc. Okay. So ultimately what you guys need to understand is that your Kc, your Kp is equivalent to Kc multiply by what? Multiply by RT. Raise the power change in number of moles. Okay, so it comes from the relationship of the relationship that I've shown on the bottom there. That's how that formula comes about. So you need to know your Kp is equal to. So of course you can try this out by just substituting in this very formula that we had here. Yeah. So if you try to substitute this part that we have for all these components, what you're going to realize is your concentrations are going to stand out. It's like let me try to show, since this video I'm trying to explain and make you guys understand what we're talking about. So okay, let's do this. So on top, where we had, remember we're saying we have A and B reacting to give us C and D, not so. And then we're saying the pressure of any given gas, given this formula, you have something like that, right? So for the products we have C, so I'll say the concentration of C multiplied by RT. Again, I'll say the concentration of what? The concentration of D and then RT, and then I'll say the concentration of what? The concentration of A, and then I'll say RT, and then the concentration of B, and then I'll say RT. Okay. Now, one thing that we can do is go to Kc. So from Kc, what we had noticed is something like this. So from Kc we said concentration of C, concentration of D, and then we can say concentration of A, concentration of B, and then these guys are raised to their stoichiometric powers, C, D, and then we have AB. So if you compare the two, you're trying to come up with a way in which these guys can kind of be equivalent, or yes, in what way can these guys be equal? In what way can we make them to be equivalent? So looking at what we have, you realize that the difference is more kind of based on the powers C and D, A and what? A and B. So you're trying to think of something that you can multiply with Kc and kind of just make up for everything that you have. Okay. And what basically are you going to have? So what you can do is, since we've seen that RT is kind of common on that part of the formula, you can introduce this and multiply it to this guy, RT. And of course, these RTs are going to be different because of the stoichiometric coefficients that you may talk about. Remember, from our formula Kp, for example, for C, the pressure of C is to the power C. So I think that's an omission that I've made there. I've made an omission. So by the way, all these are supposed to be raised to the power. This one CC, DD, AA, BB. Okay, yeah. So which tells us to say that at this point, at least it makes more sense because it's only the RT that are kind of different, not so. Everything else is the same. Okay, so everything else, if you compare it against Kc, it's the same except the RT. So you can remove the RT in somewhere. So you say RT on top. So that you just factorize out the RT, and then if you do that, you do know what when you have the same base. When you have the same base, what do you do about it? So when you have the same base, maintain the bases, and then when you're multiplying, add the powers. So you say C plus D. And then on the bottom, you do the same. So you say RT, and then you add the powers, which will give you A plus B. So when you get to divide them, it will be RT, and then it's the power on top minus the one on the bottom, A plus B. So now you notice that the C plus D is for the products, the reactants. So you can just say that is change in what? The number of moles. Change in number of moles. So this remaining part is equivalent to Kc, as you can see. So I can remove it. And ultimately your Kp becomes Kc multiplied by RT, the change number of moles. Where change in number of moles is C plus D minus A plus B. Wherefore we are saying the number of moles of your products minus the number of moles of reactants. That's if you have A. So don't worry if you've not gotten this. Just know the formula to help you. But I was just trying to show for the sake of showing. Yeah. So a change in number of moles would just be, like we said, A plus B. So A minus, sorry, to C and D that were on top. So you just add the stoichiometric coefficients of products minus the stoichiometric coefficients of reactants, and you have changed the number of moles. Raise your RT to that number of moles that you have, multiply by Kc, you'll be able to get Kp. Equivalent, you can divide the RT to the change in number of moles and find Kc. So finding Kc, you divide the other side by RT, the power change in number of moles, and that is the relationship between Kc and Kp. Okay. So now, I would also want to talk about the relationship that is there in terms of the Kc itself when you have a reversible reaction. So let's say you have this reaction, right? And then your Kc is 0.212. So given that Kc for that reaction is that, find Kc for a reversible reaction. Given for a forward reaction, that's your Kc. How do you find the Kc for the reversible reaction? So now, what you'd want to do is you would want to write the equation of the reversible reaction. So I'll start with that part for the reversible reaction. And then we have something like this. Now, if I try to write my Kc expression for the first guy there, the first reaction, we're going to have something like, for our products, we just have NO2. Now raise that to the power 2 divided by N2O4, just the power 1. And then I'll try to do the same again for the other one. This time around I have just have that as my what? And then on my products I have the same NO2, the power 2. So what you can see is, if you try to compare these two guys, what have you noticed? So I'm hoping you've noticed that on the, it's just a reciprocal, like we've exchanged them, not so. Whatever is on top is down on the other part. So that's just like a reciprocal. So if I was to put, like, on the first one, I put a 1 on top, the reciprocal, it would have to exchange from mathematically, of course. Yes. Which will now be equivalent to what? To the Kc for the second half reaction. For the second reversible reaction, that is. Sorry, I've been talking so much about electrochemistry and yeah. So therefore, we've seen that these are just reciprocals. So if I'm given a Kc value of one reaction, that is, if I reverse it, the Kc of the next reaction is going to be 1 over Kc. It is just going to be 1 divided by that. So therefore, the Kc for this reaction is 1 over 0.212, which if you divide will give you 4.72. So that's one thing that you need to understand. Now, how about if we tried to multiply? Let's say we double the moles there. Let's say if I put 2 NO4, and then it becomes 4 NO2. So what have we noticed? We've noticed that we've just doubled like everything in the first reaction there, and then how does that affect the Kc value? So all the same, we can try to write the Kc value. That is okay. We can try to write the Kc value. So for our Kc value for a first reaction, it will still be dependent on the same equation, NO2 to the power 2 over N2O4. Now if you look at the second one, my Kc value, or our Kc value, is going to be, for our product we have NO2 the power 4, and then down we have N2O4 the power 2. So what can you see? So the one that is on the bottom is bigger, right? So I can decide to factorize the 2. I'll just do this. So I'll factor out the 2. So I'll remain with 2 and 1, and then it's like I've raised everything towards the power 2. Okay. So what is inside here is equivalent to what is on top there. What this tells me is, given the Kc value of one equation, if I multiply it by 2, for me to find the Kc of the next value, I just need to raise it to the power that I've multiplied with. So in this case, since we've doubled everything, the Kc value of the second reaction is just going to be the Kc of the first reaction to the same power that we've doubled, which is a 2. And that is one thing that is very, very important under the Kc calculations that we need to understand. Okay. Now, you guys, just before I forget, you also need to understand that we have different kinds of equilibrium. We have what we call homogeneous, heterogeneous. So already so far, what we've talked about are homogeneous equilibrium. For homogeneous equilibrium, this is a case where you have all the reactants in the same phase. Let's say you have A plus B, and then C plus D, and then all these guys are just like gases. So that is an example of a homogeneous equilibrium. Hetero means different. So for heterogeneous, I can even give you an example. Okay, just like I emphasized, I said you guys need to understand that our calculations for Kc are only dependent on aqueous and gaseous states. So in this kind of a reaction, our Kc value or expression is just going to be the products so the power 2. We will not divide by anything because this is a decomposition reaction, and then this guy is what? A solid. So this is an example of what we are calling heterogeneous equilibrium. So in heterogeneous, of course, all the reactants and products don't take part in the Kc expression calculation. Okay, that's very, very important for us to just understand. Okay, so I mentioned one thing that is very important. I said our Kc calculation is only based on the concentrations of the reactants and products at what? At equilibrium. So then, what do you do in a case where they've given you a reaction with initial concentrations? So that will introduce us to a very, very important understanding of this topic. So we have hydrogen and iodine. Of course, all these are gaseous. For argument's sake, in case, yeah. So, and then we have that being produced. So all these are gases. So that's an example of homogeneous equilibrium. So now, this reaction is starting initially. Initially, as we start this reaction, our concentration is that for these two guys. So that's the way we are starting our reaction. Of course, let's say all these are molar concentrations. Now the question says, find Kc. How do you find your Kc? So we need to be very, very careful because if I say, for example, 0 there, and then I say 0 divided by everything else, Yeah, of course we know how to come up with a formula, but we need to understand how do we do it. Of course our case is, in this case you can say product, we just have that to the power 2. Reactants, we just have hydrogen and then iodide. Yeah, but this is our expression. Now the values that we need to substitute in this equation are supposed to be equilibrium what? Values. Now just to give you this idea, so initially when you're starting, if you try to calculate the constant using those concentrations, what you're finding is what we're calling the Q. Okay. Now K needs equilibrium concentrations. Okay. So that can even help you understand the relationship between Q and K. So I'll explain later. So looking at what we have, how do we find Kc? So now this introduces us to a basic idea of the ice table, which is going to be very useful under the study of equilibrium, even as we get to look at acid base equilibrium, and also looking at the solutions. Of course, looking at the solubility expression Ksp. It's also very important that you understand the ice table. So we call it the ice table to just help you remember. Okay. So in this case, I don't have enough space, so I'll just start from the data that I have. So I'll call that I, and then I can say ice. So what does this stand for? So we're calling it the ice table, and that's the way it comes out. So I for initial, C for change, E for equilibrium. So these concentrations that are going to be in the last law are the ones that we're going to use in our Kc calculations. So now, whenever we're not given any information about in some reactions, you're going to be told to say at start you are at a certain concentration, but before equilibrium. Now in this case, it seems we started purely with what? Reactants. So our initial concentration of our product was 0 at start. Now under the change here, you need to understand that when a reaction is just about to start or progressing, the reactants are supposed to reduce, and then the products are supposed to increase. So I can say, looking at the coefficients, say 1 and then 2 of the other side, so say minus. So I'll use the variable x, minus x. The other side I'll say plus 2x. So if I add a 2 there, I would have said minus 2x. Okay, that is the way we express our change. Okay, that is very, very important and very key for each one of us to just get to understand. So after you've done all that, what you just need to do is, and in most of the cases they're going to give you one of the final concentrations so that it will help you get to find the value of x. Okay, so now in this case they gave us a value of the product. So 1.87 times 10 to the power negative 3. I just submitted that in the question. So the question had given us the initial concentrations, and then they also said at equilibrium the concentration of the product was this. So meaning that we just had to fill in 0 and the 2x. So that can help us find the value of x. So the idea is your initial plus your change, just like we've written them. So I'll say 0 plus 2x is supposed to be equivalent to 1.87 times 10 to the power negative 3. And then if you grab your calculator there, it's going to be very easy for you, because I can just say 1.87 divided by 2. So I'm getting a value of 0.935. Okay. So which can just say our value of x is equal to 9.35 times 10 to the power negative 4. So what is our value of x? So since these are just minus x, we can substitute there the value of x. So 9.35 times 10 to the power negative 4. 9.35 times 10 to the power negative 4. So notice that we were already given in the question the initial concentration, the equilibrium concentration of a product. So we just need to find the equilibrium concentrations of what? Of our reactants. So now 1 times that, 1 times 10 to the power negative 3, 1 times 10 to the power negative 3, minus 9 times 9.35 times 10 to the power negative 4. So I'm getting 6.5 times 10 to the power negative 5. And then the other one, that is like 2 times 10 to the power negative 3 minus 9.35 times 10 to the power negative 4. So I'm getting 1.265 times 10 to the power negative 3. Okay. So this is what we have as our equilibrium concentrations. So now, what you just need to do, ladies and gentlemen, you need to go back to your case where you said your case is dependent on your products, of course raised to a stoichiometric power, divided by what? Divided by the hydrogen and the iodide. Okay. So you just substitute the values that you have. This guy, the power 2, divided by the product of his, and then you'll be able to calculate the value of what? Your Kc. Okay. So I think this is too much information. I hope you've understood now how we get to look at chemical equilibrium. So I hope this has made up for the class that we never had. And if you finished the video, I would want to hear from you. Just text me. I'll be very much happy to know that, because most of the people don't finish the video. So if you finish a video, you text me any question that you have. I'll be very much happy to know that you finished the video. Otherwise, look up for more questions on the ICE table, because it's very, very important, and you'll meet it in your in your questions coming.